Hello, and welcome to Vector's Software Test Symposium. My name's Tim Schneider, and I've been working with the Vector Code Test team for over 10 years. For the next 20 minutes, I'll show you how to use continuous tests to improve your code quality and increase your development efficiency. We'll start out by defining exactly what continuous test is. Then we'll look at how continuous tests can improve your code quality and development efficiency. After that, we'll look at some implementation examples and wrap up with some Q&A. Let's get started. So what exactly is continuous test? Well, continuous test is a process where we're executing automated tests as part of a delivery process. The idea is to go off and do that testing and obtain immediate feedback. So you can do technical assessment on how the software changes have affected the overall project, and possibly even get some business risk analysis done for each of these release candidates. So a continuous test result can be used by many disciplines. So program management can use them, the systems engineering team can use it, obviously the software developers can all use continuous tests to get the information they need off of their work they do. So continuous tests can incorporate multiple automated test methodologies as well. So things like software build, static analysis, unit and integration and system testing, also KPI analysis. Those are the key performance indicators like technical debt, schedule changes, things like that. Those can be very important to help run a program better and really increase efficiency. So automation is the key to improving code quality with continuous test. Different events in the development cycle should naturally trigger different levels of testing. Having an automated tool with integration for your third-party tools will help you launch these triggered events and quickly give the results back to the appropriate party. Some examples that could trigger some of these, possibly closing a support case. When you close a support case, something probably very simple should happen. We go through the KPI analysis of technical debt and scheduling, and to see where we're looking, how's our schedule on fixing bugs. We get requirements updates from a customer, and that would normally include some type of system testing that would go on. In this case, we're doing some integration and system testing to make sure that the requirements we recorded before are still valid. Okay, and then some KPI analysis for requirements traceability, scheduling, and technical debt. We could have an engineer that goes through and does a interim software commit to the SCM system. In that case, something like build analysis. So we're going to do a software build to make sure there's no bugs, do a PC lint analysis, and then we could go in to do some unit testing. And then at the back end of that, we'll do some gating. Did this software do what it's supposed to do? Are there any problems in it? And lastly, if we get a merge request or we get a release candidate ready, we may run through an entire process of the entire full build process, a full retest, which would include all the pieces of software build analysis, system and integration testing, unit testing, KPI analysis, and then scoring on the back end to see if these are really ready to go, ready to be put out. So let's look at each of these events in a little more detail. For the event of someone closing a support case, you may do some KPI analysis for defect and ticket tracking. Look at the analysis of maybe we have a decrease in open bugs. We can get information on percentage of distribution and maybe a pie chart like we're seeing. But all that can go back into further analysis of technical debt. And in technical debt analysis, if you get a nice dashboard like what we're seeing here, you can actually see some of the outliers really, really easily. Something like machine read files, very low source code count, very high technical debt. Something like send score, a lot more code, but a higher technical debt than what we would normally see, but it's still within the range. You may want to do analysis on and go and look at that. And the results are sent back to the QA manager when they're done. So you may get a package that looks like this, or just an email or report that would encompass all of this information off of a closed sales case. So we get an update of requirements from the customer. We may go through and run those system integration tests again and do the KPI analysis for requirements. So are the requirements trending in the right direction? Do we have test coverage trend? In this chart, we're seeing it, if it's up in the green or the blue, we're doing good. Down the red, not so good. So we can see in this case, we're going up and to the right, so that's really good. And then maybe we get those results sent back to the systems engineer, and they can go through and do their information back up the chain. For software commits, we may do some unit testing and static analysis. So you can see this type of information. How are we trending with code coverage? How are we trending with the failed test cases? And have we increased or decreased some of the findings from the static analysis tool? And again, those results may be delivered right back to the developer so they can see, did their code have any really negative effects on code coverage, test results, and findings. And then another big event, the pull merge request or a release candidate, that would get full testing, full release and quality gates, and then a full KPI analysis. You can go and generate this kind of information and then output maybe in a document that is suitable for your customer delivery. And then management gets those results at the end of the release. So when I think about continuous test, I always think, don't make quality wait on testing. So when you're implementing your test, you need to take into consideration how quickly your test runs. For example, if you can shave off, say, 4 seconds per unit test, and you have in the order of 2,500 tests, you're going to save 2 hours overall trying to do a full run of your test. And different platforms that you run your tests on have different trade-offs for capability and execution speed. So the first one almost everybody starts with is using these fast test platforms is host-based testing. And host-based testing, usually where folks start off, they use the native compiler for Windows or Linux, and they do native execution. These are really good platforms for doing things that don't require the hardware. So state machine testing, communication path testing, and algorithmic testing. Those 3 things are ideal for running host-based tests. The next step is to get a little closer to the hardware and maybe use an instruction set simulator or an emulator for testing. Okay, the benefits here is you're using the exact same compiler that we will be using to run on your actual hardware. It's much faster than running on hardware because it almost runs at host speeds. If you say have a small processor, you run at 25 megahertz, that's going to be really slow compared to the multiple gigahertz machines we have sitting on our desk. And these simulators and emulators are good for state machine communication and algorithmic testing, but since they're closer to the hardware, you can actually get some architectural testing, and if it's a really good ISS or emulator, you may be able to get some I/O or peripheral testing as well. And all these tests translates to when you're actually running on hardware, it's just very much slower because again, the discrepancy between the processor speeds, loading things onto the board, flashing, running over a slow JTAG, things like that can really slow down your testing. So when you're thinking about this type of thing, the faster the better. If you have to run on hardware at the end, you can start off by developing your test on the host. They're really, really fast. Then switch to a simulator to get a little more architectural. And then maybe once in a blue moon, once a week, whatever, you're running on your actual hardware. So how can we speed up even slow test platforms? We can utilize parallelization. By identifying specific tests that need to be executed and distributing them across multiple execution platforms in parallel, you can really reduce your overall execution time. And programs can start off small, maybe with one continuous test machine that has multiple processors, multiple cores. You can start scaling that up, adding in more hardware, add a test farm, and some people even go out to the cloud and run cloud-based testing. The thing you need to do, though, is once you spread out all this testing, is to aggregate the results back to a common dashboard. Okay, the current class of dashboards can really handle some basic metrics like static analysis, build results, code coverage, things like that. But they can't go very much beyond that. So the idea with these standard dashboards, and a lot of CI tools, continuous test tools, will have a common dashboard. They'll let you see the deltas from run to run. So that test results, did I fail anymore? Did I reduce the code coverage? It'll allow you possibly to look at just coverage on lines of code. And then the static analysis metrics, those really need to be on a per file basis and then rolled up so you can see exactly what's going on. Okay. Some of the more advanced dashboards that are out there can do some advanced software metrics, may do things like reliability, maintainability, HIS metrics, and even some key performance indicators for technical debt, bug fix times, resource allocation, things like that. So what happens after you've done your event that kicks off your tests, you've done the appropriate testing, what happens after that? Well, you need to have some kind of automated gating that will reject or pass the event on predefined criteria. Okay, whether they're quality gates for increased findings on static analysis, lower metrics, increased coding violations, or decreasing requirements coverage, those can be a set of quality gates that you would run on one event or another. Okay, test result gating, lower code coverage, higher test failure. If you start getting into that area, you may want to set a rejection criteria for those. You may not want to say no lower coverage because some of the code you change may change the flow of the overall program, and naturally have some lower coverage. But you should be able to dial those in. So lower code coverage, higher test failure would something that like the test result gating would cover. And then for like some of the more advanced dashboards, some of the more advanced things you can do, the KPI gatings, where if you get a much higher technical debt, or you're looking at schedule overruns or increase in software bug reports in this time frame, you may want to say, okay, let's hold off and let's go back and do some more analysis. The idea is these automated gates really are predefined, so you don't have to say, oh, is this one's good enough, we'll let that one slide. It's there, and you pass or fail. Now let's look at how continuous tests can improve your development efficiency. So making your development more efficient really comes back to picking up the bugs early. So let's look at the scenario here where a developer makes some software changes. He commits that change to SCM, and that SCM tool triggers a test run. We're going to get the continuous test machine, whether that's the machine down the hall or up in the cloud. It's going to go through and identify the tests that are required to test that portion of software that you've changed. It's also going to run any tests that could prove out potential side effects to software change. And we call that change-based testing. Now, the idea with change-based testing is if I make changes to A, the C file, the CPP file A, it's going to have direct effects on some of the tests that are within its purview. If you make tests, code changes to B, it's going to naturally have some of these down here that are directly affected by that code change. And then if you don't touch C, it still could have potential test code changes, these side effects. So when we make changes to A and B and nothing to C, and we rerun these tests, we shouldn't have to run all the tests that are there, all 45 tests that are there. We should be able to just run a small percentage that are just targeting the changes you made. So from the green, from A, we can see test 2, test 6 through 10, test B8, C3, and C12. Those tests, based on where those tests ran previously, they're going to need to be rerun. And then for B, we're going to need A14, B2, B11 through 15, and then C15 as well. But you can see we've reduced the overall amount of testing probably by 2/3. So you have about 1/3 of much of what was there. Okay, and that's the idea of identifying the specific tests that need to be run to really, again, get these tests run quickly and get the results back to the developer. And then we take those tests and we can parallelize them. Okay, whether it's the host or the simulator or the hardware based, we parallelize those tests, spread them across 15 machines, run those 15 tests, and get that data back as soon as possible. And then in this specific case, the results are emailed back to the engineer within minutes. He can go get his coffee, freshen it up, and look and see, I have some side effects. I need to go alert the other team that my changes, which are all good, has some potential side effects on them. And that's what the engineer will do. You do the assessment to see if more changes are needed. Okay. If those changes are within that engineer's purview, he can make those changes, resubmit. Otherwise, he can go alert to the other team to what potential problems could be there. Now let's look at this in some real world examples. So in this case, we're going to be having some tools available to us. So we'll use Jenkins as our continuous test machine. VectorCast C++ will be our unit and code coverage. VectorCast QA will be used for code coverage and system testing. Canoe is our multi-bus simulation and testing tool for ECUs. PCLint will be our static analysis tool. Score, which is that multi-tool dashboard KPI analysis platform. MATLAB Simulink for model development and testing. And then for code coverage on those Simulink models in SIL and PIL mode, in processor in the loop and software in the loop, we'll use the MATLAB toolbox for VectorCast. So let's look at this as a Jenkins pipeline example for a support cases being closed. So in this event, the engineer here, he's all happy. He's closed his support case, and he triggers that going out to the continuous test machine. Again, it's going to do the scheduling and update the software bugs and recalculate all the technical debt. And he's going to send that over to the QA manager. That'll be automatic. This QA manager is obviously happy. We're getting rid of software bugs and making his KPIs look good. In this case, we're getting a requirements change from a customer. We can see our systems engineer down here. She's really happy to get these additional requirements from the customer. So she's going to go in and update the requirements management system. And once she updates that, we'll get a run of system and integration testing. That'll be using the tools that we've specified already. Then it's going to go back through the KPI analysis, but this time for requirements traceability. The score analysis will do requirements traceability, do scheduling, and again update that technical debt. And at the end, the results are pushed back to a customer relations manager, and he can go through and say, we've implemented we've added these new requirements. Here we are on coverage for those. We're looking pretty good. So he's happy. This next one is Jenkins pipeline again. The developer commits to a private branch. So when he does that, he makes his changes for the day. He's going to go through and he's going to push out to his private branch on the SCM server. That server will then kick off a build that's going to be a software build and analysis. So it's going to use this compiler to do the build. It's going to use PCLint Plus to get those results back. You're going to go through and parallelize all your unit tests, and hopefully you get those pushed out there using change-based testing to, again, minimize just exactly what he needs to focus on. Because this guy just changed 2 lines. He doesn't want to go through 4 hours of testing to see if he's messed something up. So his 2-line code change, he's going to go in and push that in, make sure just the ones that need to run are running, and then do some simple analysis. Again, the system will automatically do this. He won't have to do this. But he can look at a build gate. Did this build without any errors or warnings? That may be something you look at. With the PCLint gate, did we get more or less findings for static analysis issues? With the test result gate, did we get more test failures or lower code coverage? Those are all things that we can do very simply on something like Jenkins. We don't need to go out to a special dashboard. This is more private. This is more for the engineer himself to get those results. Everybody's happy. So the last example we've been talking about is the full build. And this is for something major, like a release milestone, a factory acceptance test, and the program manager will call out for the testing, kicking off that event, a release milestone test. And basically what's going to happen is it's going to run through the full pipeline. So the engineering manager, he may not push the button to start, but he'll send an email to the test team saying, give me a full run of this. And they're going to do the PC lint analysis, the static analysis, system and integration and unit testing, whether they're calling out for a MATLAB with the VectorCast toolbox to do their software in the loop or processor in the loop, model verification, pull up QA and Canoe to get that integration testing done, maybe using their own test bed for the factory acceptance testing, getting code coverage out of that, bring in the unit testing again, having those run in parallel, and then doing your KPI analysis with SCORE. Do we have more software bugs? Is the schedule looking good? Did the technical debt explode now that we brought in all these various pieces? And then again, applying the gating that would be appropriate for this event. So all the quality gatings we talked about before, the test result gatings, the KPI gates, they all get done. And again, this is automatic. This may be your longest test. This may be an overnight run. But in the end, everybody's happy. Everybody's giving themselves high five. The team know they did a great job. And it's all because we've gone through the steps along the way to get this continuous test implemented. So we've gone through the steps of requirements testing, software bugs, release candidates, system integration. And a lot of these obviously have been months or years in the making to get everything automated to the point where it can just be run at the push of a button. But those are things you really need to be looking at with continuous test. So what do I want you to take away from the idea of using continuous test to improve your code quality and increase your development efficiency? So the first thing is continuous test has to be automated. You have to select the appropriate tool at the beginning. These tools that you have, your third-party tools, have to be able to plug in and give information to the CI platform or to your dashboard. And getting the reporting out as soon as possible is very important. Okay, using various triggers from the tools that you already have to trigger events that go into your continuous test platform could be something as very small as a software commit or very, very large like a requirement change that requires much larger testing. And in the end, the automatic decision making via gating, quality gating, test gating, KPI gating is essential. And again, last part, don't make quality wait on testing. Testing must be fast. Test only the areas that have changed. And if you can have a scalable parallel architecture, that's going to be the best thing long term for getting the increased efficiencies that you're looking for. So this brings me to the end of my presentation on continuous test and how it can improve your code quality and improve your development efficiency. I look forward to taking your questions over in the Q&A. So let's go.